Today, we're diving into the world of design of experiments, or DOE for short. Now, you might be wondering why this topic is so important. Well, let's think about it like this. Imagine you own a high-ticket item store and want to boost sales by tweaking different factors, such as pricing, advertising, or product placement. How do you know which changes will make the biggest impact? That's where DOE comes in. It helps us figure out how changing one or more variables can influence outcomes. So, let's break this down step by step. First off, what exactly is design of experiments? It's a structured method used to determine the relationship between factors affecting a process and the output of that process. In simpler terms, it's about making smart decisions based on data rather than just guessing or relying on intuition. Now, let's look at how DOE works in practice. We start by identifying all the potential factors that could affect our outcome, which we call independent variables. For instance, if we're running a bakery, these might include things like oven temperature, baking time, type of flour used, and so on. Next, we design experiments where we change one or more of these factors at a time to see how they impact the final product quality. The key here is that DOE isn't just about randomly trying different combinations. It's about strategically selecting which experiments to run based on statistical principles. This way, we can efficiently determine which variables have significant effects and which ones don't matter as much. It's like playing chess. Instead of checkers, every move has purpose. Another important aspect of DOE is replication. We repeat our experiments under similar conditions to ensure that any observed effect isn't just due to chance, but is consistent across multiple trials. This helps us build confidence in the results and makes our conclusions more reliable. Now, let's talk about how DOE benefits businesses beyond just identifying factors affecting product quality or sales. By using DOE techniques, companies can optimize processes, reduce waste, improve efficiency, and ultimately save money. It's like tuning up your car to run smoother and use less gas. Everyone wins. So there you have it. Design of experiments is a powerful tool for understanding and optimizing processes across various industries. Whether you're dealing with complex manufacturing systems or simple everyday tasks, DOE can help uncover the most impactful changes to make. In conclusion, DOE isn't just about running experiments, it's about making smarter decisions based on data-driven insights. So next time you're faced with a problem that needs solving, remember to think like a scientist and design an experiment to figure out the best solution. All right, everyone. Today we're going to dive into why design of experiments, or DOE for short, is so crucial in process improvement. Picture this. You're trying to make your product better, cheaper, faster. You know there are factors that influence the outcome, but how do you figure out which ones really matter and how they interact with each other? That's where DOE comes into play. DOE helps us understand these interactions by systematically varying multiple input variables at once instead of changing one factor at a time. This way, we can pinpoint exactly what's affecting our process and how much. It's like peeling back layers to get to the nitty-gritty details that really impact quality or efficiency. Let's take an example. Imagine you're optimizing a chemical reaction in your lab. You might have factors like temperature, pressure, concentration of reactants. Without DOE, you could spend weeks tweaking one variable at a time but miss out on discovering how these variables work together. With DOE, you can run experiments to see the combined effect and identify which settings give you the best results. Now, why is this so important? Well, it helps reduce waste by identifying only the key factors that need adjustment. It also speeds up your development process because you're not wasting time on unnecessary changes or adjustments. Plus, it provides a solid foundation for continuous improvement since you have clear data on what works and what doesn't. In essence, DOE is like having a map when navigating through complex process improvements. It guides you towards optimal settings with minimal guesswork and trial and error. This means less time wasted and more effective process adjustments, leading to better products at lower costs. So next time you're faced with improving a process, consider using DOE. It's a powerful tool that can help streamline your efforts and lead to significant improvements. All right, let's dive into understanding variability and its impact on processes. Think of it like this. Every time you brew coffee, there might be slight differences in how strong or bitter it tastes, right? That's because brewing coffee isn't an exact science. The water temperature, grind size, even the roast can vary slightly each time. This idea applies to all kinds of processes. Now, let's break down what variability means. Simply put, it's the degree to which individual measurements within a group differ from one another or from the mean value. So when we talk about coffee brewing, if you measure your water temperature and grind size every time, there'll be some variation each time you make a cup. Why does this matter? Well, understanding variability helps us improve processes by identifying where inconsistencies might occur. For example, in manufacturing high-ticket items like luxury watches, even small variations can lead to significant quality issues or customer dissatisfaction. By studying these variances, companies can tweak their methods to reduce defects and boost overall product quality. Let's take a look at how this plays out in real-world scenarios. Imagine you're running a bakery that specializes in artisanal bread. Each batch of dough might have slight differences due to variations in flour batches or yeast potency. These minor changes could affect the final texture, taste, or even baking time needed for each loaf. By tracking these variables and making adjustments accordingly, bakeries can ensure consistency across all their products. But variability isn't just about identifying problems, it's also a tool for improvement. When we measure how much things vary, we gain insights into which factors are most influential in the outcome of our processes. This allows us to focus on those key areas and work towards minimizing unwanted variations. So, what can you do with this knowledge? Start by observing your own process closely. Look for patterns or trends that might indicate where variability is having the biggest impact. Then, make small adjustments based on these observations and see how they affect your end result. Over time, you'll likely notice improvements in consistency and quality. In conclusion, understanding variability isn't just about spotting problems. It's about leveraging this knowledge to enhance processes and achieve better outcomes. Whether you're brewing coffee or producing high-end goods, recognizing where variations occur can lead to significant improvements in efficiency and customer satisfaction. All right, everyone. Today we're diving into an important topic in statistics, measures of central tendency and dispersion. So let's start with the basics. What do these terms mean? Well, measures of central tendency are like the heart of our data set. They give us a sense of where the center lies. The three main types are the mean, median, and mode. The mean is simply the average. You add up all your numbers and divide by how many there are. It's great for giving an overall picture, but can be skewed if there are extreme values or outliers in your data set. Then we have the median, which is like the middle child of our data set. To find it, you line up all your numbers from smallest to largest and pick the one right in the center. This is useful when dealing with skewed distributions because it's less affected by those outliers than the mean. Lastly, there's the mode. That's just the number that appears most often in your data set. It's pretty straightforward, but might not always exist if all your numbers are unique or appear equally frequently. Now let's talk about dispersion. This tells us how spread out our data is from the center. We're looking at things like range, variance, and standard deviation here. The range is super simple. It's just the difference between your highest and lowest values, but it doesn't tell us much about everything in between. To get a better sense of dispersion, we often use variance or standard deviation. Variance calculates how far each number in the set is from the mean on average. Then, to make that easier to interpret, you can take the square root of the variance and get your standard deviation. It gives us an idea of how much our data typically deviates from the mean. So why do we care about all this? Well, understanding central tendency helps us quickly summarize a dataset with just one or two numbers. And knowing dispersion tells us if our data is tightly clustered around that center point or spread out over a wider range. This information can be crucial in making decisions based on your data, whether it's deciding which product to stock more of at high-ticket prices or figuring out how long you'll need to spend ironing the nitty-gritty details of a project. All right, so to recap, measures of central tendency help us find that sweet spot in our data set, while measures of dispersion tell us how spread out those numbers are from that center. Together, they give us a pretty good picture of what's going on with our dataset and can guide us in making informed decisions based on the information we have. That wraps up today's lesson on measures of central tendency and dispersion. Thanks for joining me. I hope you feel more confident about tackling these concepts now. All right, everyone, let's dive into one of the most crucial aspects of any successful experiment: defining objectives and metrics. When you're planning your experiment, think about it like setting sail on a boat towards an island. You know where you want to go, but how do you get there? That's where your objectives come in. Objectives are specific goals that tell us what we aim to achieve through the experiment. For example, if we're testing a new fertilizer for crop growth, our objective might be to increase yield by 20. So, it's clear and measurable, no guesswork involved. Now, metrics are the tools we use to measure progress towards those objectives. If we're measuring yield, our metric could be kilograms of produce per hectare. We track these numbers throughout the experiment to see if we're meeting our objective. When setting your objectives and metrics, remember a few key points. Firstly, they need to be specific, not vague. Secondly, measurable, you should be able to quantify them. Thirdly, achievable, don't set yourself up for failure by making impossible goals. Fourthly, relevant, make sure they align with your overall experiment aims. Lastly, time-bound, give yourself a timeline to reach these goals. By following this SMART framework, you'll create clear and realistic objectives that guide the direction of your experiment. Remember, if an objective isn't measurable or achievable, it might need adjustment. Another important consideration is choosing metrics that accurately reflect changes in your system. For example, if you're studying customer satisfaction for a new product, surveys could be your metric rather than just sales figures. This way, you capture the qualitative aspect as well. All right, so we've covered defining objectives and selecting appropriate metrics. Remember to keep them specific, measurable, achievable, relevant, and time-bound. These steps ensure that your experiment has direction and purpose. All right, everyone. Welcome back to our lesson on identifying factors and levels in your experiment. So today, we're going to dive into what these terms mean and how you can apply them effectively in your own research projects. Let's start with understanding what a factor is. In the context of experiments, a factor refers to any independent variable that you manipulate or change to observe its effect on another variable. For example, if you're studying how light exposure affects plant growth, light exposure would be one of your factors. Now, let's talk about levels within these factors. Levels are specific values or settings for each factor in your experiment. If we use our previous example where the factor is light exposure, its levels might include different durations such as 4 hours, 8 hours, and 12 hours per day. So every time you change one of these elements, you're looking at a new level. To break it down further, imagine you're testing two factors: type of fertilizer and watering frequency. The types of fertilizer could be organic or chemical. Those would be your levels for that factor. Watering frequency might have levels such as once daily, twice daily, and every other day. When planning your experiment, identifying these factors and their respective levels is crucial because it helps you structure your research properly and ensures you're gathering meaningful data. It's important to choose relevant factors based on what questions you want to answer and which elements could potentially influence your outcome. For instance, if you're investigating how temperature affects yeast fermentation rate, temperature would be a key factor with levels like cold, room temperature, and hot. Also remember, the number of levels for each factor should depend on the scope of your study and resources available. Too many levels might complicate things or require more time than you have, whereas too few could limit the depth of your analysis. All right, let's recap quickly. Factors are independent variables that we change in our experiment to see their impact on another variable, and levels are specific values within those factors. By carefully selecting and defining these elements, you can better understand how different aspects might influence your results. So next time you design an experiment, take a moment to clearly identify your factors and their corresponding levels. This step-by-step approach will make sure you're setting up your research for success. That's it for today's lesson on identifying factors and levels in experiments. I hope this gives you a clearer understanding of these key components and helps you plan more effective studies. All right, everyone. Today, we're diving into an exciting topic in experimental design: full factorial design. This is one of those nitty-gritty details that can really elevate your understanding of how experiments work and help you make better decisions based on data. So, what exactly is a full factorial design? Well, it's essentially a method used when we want to study the effects of multiple factors and their interactions on a response variable. Picture this. Let's say we're testing how different ingredients affect the taste of our coffee. We could have 3 factors like roast level light or dark, milk type whole or almond, and sugar amount none, small, medium. A full factorial design would involve setting up all possible combinations of these factors to see which one makes the best cup of coffee. Now, why do we use this method? Because it allows us to not only understand how each factor affects our response, but also how they interact with each other. This is super important because sometimes a change in one factor can have a completely different effect depending on another factor's value. Let's break down the process step by step. First, identify all your factors and levels. For instance, if you're testing 3 factors, each at 2 levels, that gives us 8 total combinations to test. Next, set up your experiment by running trials for every possible combination of these factors. It can get a bit complex as the number of factors increases, but modern software tools make this much easier than it used to be. Then comes data collection and analysis. Here's where you'll use statistical methods like ANOVA analysis of variance to determine which factor combinations have significant effects on your response variable. Finally, based on these analyses, you can draw conclusions about what works best or worst in terms of achieving your desired outcome. One thing to keep in mind is that while full factorial designs are powerful, they do require a lot of resources and time as the number of factors grows. For example, if we had 5 factors at 2 levels each, we'd need 32 trials. That's why it's important to carefully consider whether this design fits your needs or if you might benefit from other types like fractional factorial designs. So there you have it, a brief overview of full factorial design and how it can help you better understand the relationships between factors in your experiments. Remember, mastering these techniques will make you much more adept at designing effective studies that yield meaningful results. That's all for today. I hope this gives you some valuable insights into full factorial designs and inspires you to apply them in your next project. All right, let's dive into the world of fractional factorial design and see how it can help us make better decisions when dealing with multiple factors in an experiment or study. Now, imagine you're testing various ingredients for your new recipe and want to know which ones really impact taste. You've got a list of potential ingredients, but trying out every possible combination would be overwhelming. That's where fractional factorial design comes in handy. Fractional factorial design is like taking shortcuts when exploring all the possibilities. It lets you test fewer combinations while still understanding the main effects and interactions between factors. It's particularly useful for high-ticket items or complex scenarios where running a full factorial design would be cost-prohibitive or time-consuming. Let's break it down. In a full factorial design, if we have 3 factors each with 2 levels, that gives us 8 combinations to test. But with fractional factorial design, we can reduce this number while still capturing the most important information about how these factors interact. For instance, we might choose only half of those combinations, making our job much easier. To do this effectively, you need to understand aliasing. It's a bit like when two things sound alike, but mean different things in your experiment. Certain factor effects can be aliased with each other, so interpreting the results requires careful consideration and knowledge about which factors are interacting. Now, there are various types of fractional factorial designs depending on how many levels and factors you're dealing with. For example, a 2kp design where k is the total number of factors and p is the fraction used to reduce the number of runs. The key here is choosing the right fraction so that important interactions are not confounded. In practice, this means setting up your experiment carefully to ensure you're capturing the most impactful factor effects while minimizing unnecessary tests. By doing this, you can efficiently pinpoint which factors really matter and optimize your process or product accordingly. So next time you're faced with a complex set of variables in your study or experiment, remember fractional factorial design as an effective way to streamline your approach and get meaningful results without sacrificing too much accuracy. Today, we're diving into the fascinating world of design of experiments, or DOE for short. And one of the key concepts we'll be exploring is the role of randomization in these experiments. So let's get started. Randomization plays a pivotal role in DOE because it helps to minimize bias and ensures that our results are reliable and valid. By randomly assigning treatments or conditions, we reduce the chances that any particular sequence of events influences our outcomes unfairly. For example, if we're testing different types of fertilizer on plant growth, simply alternating between two types might lead us to conclude one is better due to timing rather than actual effectiveness. But why do we need randomization? Well, imagine you're flipping a coin and trying to ensure it lands heads up more often than tails. If each flip isn't truly random, the results become predictable and skewed. Similarly, in experiments, if factors aren't randomized properly, certain patterns might emerge that don't reflect true cause and effect relationships. Now let's look at how this works practically. When setting up an experiment, we first identify all our factors or variables and their levels. Then, through a process called randomization, we assign these different combinations to experimental units in a way that ensures no pattern is followed. This could be done manually, but often software tools are used for larger experiments. Randomization helps us account for external factors we might not even know about. Think of them as hidden variables that could sway our results if not managed properly. For instance, temperature fluctuations or slight variations in soil composition could impact plant growth differently over time without proper randomization. Another benefit is that it allows us to make accurate statistical inferences. When data points are randomly distributed across treatments and conditions, we can use various statistical tests with more confidence, knowing the results aren't biased by any underlying pattern. So in summary, randomization is crucial for ensuring our experimental design leads to valid conclusions about cause and effect relationships. It helps eliminate bias, accounts for hidden variables, and allows us to make accurate statistical inferences from our data. There you have it. That's how randomization plays a key role in DOE experiments. All right, everyone. Today we're diving into an exciting topic, understanding replication and its benefits. So let's get started by thinking about something simple yet powerful: copying information. Whether it's sharing files or backing up your data, replication plays a crucial role in making sure that information is accessible wherever needed. Replication is essentially creating copies of data so they can be used independently or to provide redundancy and improve availability. It works like this. You have your primary source of data, let's call it the master copy, and then you create one or more replicas from it. These replicas are exact duplicates that help ensure continuity in case something happens to the original. Now, why is replication so beneficial? Well, first off, it enhances availability. If your main database goes down for whatever reason, you can quickly switch over to a replica without losing service. This way, downtime is minimized and users aren't left waiting. Another big advantage of replication is improved disaster recovery. In case of natural disasters or hardware failures, having replicas in different locations means your data stays safe and accessible. It's like having backups of backups. Also, replication helps with scaling performance. By distributing read traffic across multiple replicas, you can handle more load without overburdening any single server. Let's take a look at how this works in practice. Imagine an e-commerce site that relies heavily on database access for transactions and inventory management. With replication, they could have their main database located close to where most of the users are, and then create replicas in other geographic regions. This way, no matter where someone is shopping from, they get fast response times because their requests are served by a nearby replica. Replication also supports analytics and reporting needs. You can run heavy data processing tasks on replicas without affecting the performance of your production systems. It's like having dedicated workers handle the tough jobs while others focus on serving immediate customer needs. There's another neat benefit: it simplifies maintenance tasks. When you need to upgrade a database or apply patches, you can do so on one replica at a time, ensuring minimal downtime and risk-free updates. So there you have it. Replication offers significant benefits by enhancing availability, improving disaster recovery capabilities, supporting scalability, aiding analytics processes, and streamlining system maintenance. It truly is an invaluable tool in modern data management strategies. That wraps up our discussion on replication today. I hope this gives you a clearer understanding of how essential it is for keeping your systems running smoothly and reliably. All right, everyone. Welcome to our session on ANOVA Basics for Design of Experiments, or DOE. Now, when it comes to understanding how different factors impact your results in experiments, ANOVA is like the secret sauce that helps you cut through all the noise and get down to the nitty-gritty details. So let's dive right into what ANOVA actually means. It stands for Analysis of Variance, which sounds a bit intimidating, but it's really just about comparing averages and seeing if they're significantly different from each other. We use ANOVA when we want to compare more than two groups or treatment conditions in our experiment. Here's the kicker, though. ANOVA does this by breaking down the overall variability into components that can be attributed to different sources, such as differences between group means and within-group variability. This way, you can see if your experimental factors are really having an effect or if it's just due to random variation. Now, there are a few types of ANOVA designs like one-way, two-way, and factorial ANOVA. Each type depends on the number of independent variables involved in your experiment. One-way ANOVA is used when you have only one factor being examined, whereas two-way or factorial ANOVA involves multiple factors. The cool thing about ANOVA is that it not only tells you if there's a significant difference, but also helps you understand which specific means are different from each other through post-hoc tests. This is really handy because sometimes even though the overall test shows significance, you might have different group comparisons to make. All right, let's quickly touch on how ANOVA fits into DOE. When setting up your experiments, ANOVA helps you determine if the factors and their interactions are statistically significant or not. It guides you in optimizing process parameters by identifying which ones really matter for improving quality or reducing variability. To sum it all up, ANOVA is a powerful tool that helps us make sense of experimental data and draw meaningful conclusions about our factors. By breaking down variance into components and testing hypotheses about means, ANOVA provides insights that are crucial for successful DOE projects. So there you have it, the basics of ANOVA in DOE. Hope this gives you some food for thought and paves the way for more insightful experiments. All right, everyone, let's dive into interpreting ANOVA results to identify significant factors in our data sets. When we conduct an analysis of variance, or ANOVA, we're essentially checking whether there are any statistically significant differences between group means. So imagine you have 3 different types of fertilizer and want to see which one grows tomatoes better. You'd run an ANOVA to compare the average growth across these groups. First off, let's talk about the F statistic. This is a key value in ANOVA that tells us whether our null hypothesis, which states there are no differences between group means, should be rejected or not. If your F statistic is large and its associated p-value is small, it indicates that at least one of your groups has a mean significantly different from the others. Next up, we need to look closely at the p-values for each factor in our ANOVA table. A p-value less than 0.05 typically means there's strong evidence against the null hypothesis, suggesting the factor is significant. But don't just stop there. Also consider effect sizes and confidence intervals to get a fuller picture of what's going on. Another important aspect is post-hoc tests. These help us pinpoint exactly which groups differ from each other after finding that at least one group mean differs significantly from others in our initial ANOVA. Common choices include Tukey's HSD or Bonferroni corrections, depending on your specific research question and sample sizes. Lastly, don't forget to check assumptions like normality and homogeneity of variance for accurate results. If these aren't met, you might need to adjust your analysis approach. So in summary, interpreting ANOVA results involves looking at F statistics and p-values, understanding effect sizes, conducting post-hoc comparisons when needed, and ensuring all statistical assumptions are satisfied. This process helps us confidently identify which factors significantly impact our data. Today, we're diving into interaction plots to help us understand factor effects in our data analysis projects. Interaction plots are like visual storytellers, showing how different factors interact and influence each other. They're especially helpful when you have two or more categorical variables and want to see their combined impact on a response variable. Let's start by laying out the basics. An interaction plot typically has one factor on the x-axis and another factor represented through lines of varying colors or styles. The y-axis shows the response values for each combination of factors. For example, if we're testing different types of fertilizer factor across various soil types factor B, our interaction plot would visually demonstrate how these two factors work together to affect plant growth. Now, why do we care about this? Well, understanding factor effects is crucial in many fields from agriculture to marketing. For instance, marketers might use interaction plots to see if a particular advertising strategy works better for certain demographics or product types. It's all about uncovering the nuances that help us make smarter decisions and predictions. All right, let's walk through an example step by step. Suppose we have two factors, the type of fertilizer used and whether it was applied in wet or dry conditions B. We want to know if these factors interact differently depending on their combinations. Our interaction plot will show each combination as a separate line. To create our plot first, we need to organize our data into columns for each factor and the response variable, which could be plant growth measured in inches. Then, using a tool like Excel or R, we can easily generate an interaction plot with just a few clicks. When interpreting the plot, look for any crossing lines or diverging trends. These indicate interaction between factors. For example, if one line is higher than another only at specific factor combinations, that tells us there's an interaction effect happening. It's important to note that if the lines are parallel or nearly so, we can assume no significant interaction, meaning each factor operates independently of the other when it comes to affecting our response variable. However, if they cross over or diverge significantly, then we know there is indeed a notable interaction effect going on. So why should you care about all this? Well, understanding these interactions helps us optimize processes and improve outcomes in real-world scenarios. For instance, knowing that a particular fertilizer works best under specific conditions could lead to better crop yields for farmers. In conclusion, interaction plots are invaluable tools when it comes to visualizing how different factors interact and impact each other. By mastering them, we can uncover hidden relationships between variables and make more informed decisions in our analyses. Today, we're going to dive into the world of plot analysis and explore something really important, the main effect plot. So let's get started by understanding what exactly it is. The main effect plot in literature or storytelling refers to how the primary events influence the overall narrative and impact characters, themes, and the story's outcome. Now, why do we care about this? Well, analyzing the main effect helps us understand the core elements that drive a story forward and shape its meaning. It's like looking at the backbone of a plot, all the big things happening that make everything else possible or meaningful. When we dissect these key points, it gives us insight into why certain events are significant. Let's take an example to see how this works in practice. Imagine you're reading a mystery novel where the detective solves a crime. The main effect here could be the discovery of clues leading to the arrest of the criminal. This event is pivotal because it resolves the central conflict and ties together all other subplots and character developments. To analyze the main effect plot, we look for key events that change the direction or outcome of the story. We ask ourselves, what happens next? How do these events impact characters? Do they affect future actions or reveal deeper truths about the narrative? This analysis isn't just academic, it's practical too. It helps readers understand and appreciate stories better while also improving our own storytelling abilities if we're writers. By focusing on main effects, we learn to craft compelling narratives that resonate with audiences. So, as we conclude this discussion today, remember, the main effect plot is crucial for understanding how a story unfolds and what makes it impactful. Whether you're reading or writing stories, keeping an eye out for these pivotal events will enrich your appreciation of literature. That's all for now. I hope you found this exploration into the main effect plot both enlightening and engaging. Today, we're diving into an exciting topic that's going to help us optimize experiments and processes like never before. Response surface methodology, or RSM for short, is a statistical technique used to find the optimal settings of factors that affect a response variable. Now, let me break this down for you in simple terms. Imagine you're baking cookies and want them to be as delicious as possible. You might adjust things like oven temperature, baking time, and ingredient ratios until you get just the right mix. RSM works similarly, but on a much more complex level, helping professionals across various fields fine-tune their processes to achieve peak performance. So how does it work? Well, RSM involves designing experiments where factors are varied systematically to understand how they impact the response variable. It's like conducting a series of experiments in which you change one factor at a time while keeping others constant to see what effects each has on your outcome. Then, using statistical analysis, we create models that predict responses based on different combinations of these factors. The beauty of RSM is its ability to identify not just the best settings, but also how these factors interact with each other. For example, increasing one factor might improve results up to a point, but then start degrading them if pushed too far. By understanding these interactions, you can pinpoint where your process performs at its highest. Now, let's talk about why RSM is so valuable. It helps save time and resources by minimizing the number of experiments needed to optimize processes. Plus, it provides insights into how changes in one factor might affect others, which can be crucial for troubleshooting and improving efficiency. In practice, RSM is used in a wide range of fields from pharmaceuticals to manufacturing, where optimizing processes leads to better products or services. Whether you're trying to produce high-ticket goods more efficiently or perfecting the nitty-gritty details of a chemical reaction, RSM can help streamline your efforts and achieve optimal results. So there you have it. Response surface methodology is an incredibly powerful tool for experimentation optimization. By following these steps, you'll be well on your way to improving processes and achieving those desired outcomes in no time. Today, we're diving into Taguchi methods for robust, designing and exciting approach to engineering that helps us create products and processes that are resilient to variations in their environment or use. So let's get started. Taguchi methods were developed by Junichi Taguchi, who wanted to improve product quality through statistical techniques. The core idea is to design systems that maintain performance even when faced with unexpected changes. Think of it as building a car that runs smoothly whether it rains or shines. Now, imagine you're designing a high-ticket item like an iPhone. You want this device to work perfectly under all conditions, not just in ideal settings, but also during those times when things aren't so perfect. That's where Taguchi methods really shine. They focus on reducing the impact of variations and making your product or process more robust. To do this, we start with the concept of quality loss functions. These help us measure how much deviation from a target value impacts overall quality. By identifying these losses early in the design phase, we can address potential issues before they become major problems later on. Then comes parameter design. This involves choosing optimal settings for your design factors to minimize variation and maximize performance consistency. For example, if you're designing a car engine, you might focus on variables like fuel injection timing or air-to-fuel ratio to ensure consistent performance across different driving conditions. Another key aspect is robustness testing. Here, we simulate real-world scenarios to see how well our design holds up against variations, things like temperature fluctuations, humidity changes, or mechanical stresses. By doing this, we can fine-tune our designs for better overall reliability and durability. Taguchi methods also emphasize the importance of signal-to-noise ratios. This helps us understand which factors are most influential in determining performance consistency. For instance, if you're designing a sensor, a high signal-to-noise ratio means it's less likely to be affected by background noise or interference. By incorporating these techniques into our design process, we can create products that not only perform well, but also maintain their quality over time and under various conditions. This is especially important in today's fast-paced world, where consumers expect reliable performance every single time they use a product. In conclusion, Taguchi methods offer us powerful tools for designing robust systems capable of handling real-world variability with ease. By focusing on reducing losses due to variations and optimizing design factors through careful experimentation and analysis, we can build better products that stand the test of time and conditions. So next time you're faced with a challenging design problem, think about how Taguchi's approach could help you tackle it, ensuring your final product is not only excellent, but also consistently reliable in any situation. All right, everyone, let's dive right into today's topic on conducting successful design of experiments, or DOE, in industrial settings. When you think about it, DOE is like detective work for engineers and scientists. We're trying to figure out which factors really impact the outcome of our processes or products. First off, let's talk about defining your objectives clearly. What are we aiming to achieve with this experiment? Is it improving product quality, reducing costs, or increasing efficiency? Setting clear goals helps us focus on what matters most and guides our entire DOE process. Next up is identifying the factors that could influence the outcome of your experiment. These might include things like temperature settings, material types, or processing times. We need to decide which ones are crucial for testing and which can be held constant. Then comes choosing the right experimental design. This involves deciding how many runs you'll do, what order they'll happen in, and whether there will be any replication or center points. It's like planning your route before going on a road trip. It saves time and ensures you don't miss anything important. After that, we need to set up our experiment carefully. This means making sure all the equipment is calibrated properly and that everyone understands their roles and responsibilities. The nitty-gritty details here can make or break an experiment. Once everything's ready, it's time to run the tests. Collect your data meticulously. Accuracy and consistency are key at this stage. It's also important to note any anomalies or unexpected results as you go along. After collecting all your data, the analysis phase begins. Here we use statistical tools like ANOVA or regression analysis to identify which factors have a significant impact on our outcome variable. This helps us pinpoint areas for improvement and potential optimization. Finally, once we've analyzed everything, it's time to implement those improvements in real-world settings. This could involve tweaking processes, changing materials, or adjusting equipment configurations based on what we learned from the experiment. So there, you have it: defining objectives, identifying factors, choosing a design, setting up carefully, running tests meticulously, analyzing results thoroughly, and then implementing changes effectively. These steps form the backbone of any successful DOE experiment in an industrial environment. Remember, DOE isn't just about finding answers, it's also about learning and refining our processes over time. So keep experimenting, stay curious, and don't be afraid to ask what if. All right, everyone, let's dive into this case study analysis, where we're going to apply our knowledge of design of experiments, or DOE, in real-world scenarios. Now, DOE is like a powerful tool that helps us understand how different factors influence an outcome. It's used everywhere from manufacturing processes to improving product designs. So today, we'll look at a high-ticket item scenario. Let's say we're designing a new smartphone. The goal here is to optimize the battery life while maintaining other key features. We have several factors that could impact this: screen size, processor speed, and the material used for the battery itself. Each of these has different levels or settings. First off, we'll set up our experiment using full factorial DOE, since all factors are equally important here. This means we'll test every combination of each factor's level to see how they interact with one another. Now, let's move on to data collection. We'll need a good sample size to ensure the reliability of our results. Each smartphone prototype will be tested under similar conditions, and battery life measured in hours. Once all the data is collected, we'll analyze it using statistical methods. This could include ANOVA, or analysis of variance, which helps us see if there are significant differences between group means, or regression analysis to understand relationships better. After analyzing our data, we'll identify key factors that significantly impact battery life and adjust accordingly. For instance, maybe a smaller screen size paired with a faster processor yields the best results. We might then recommend further testing of prototypes based on these optimized settings. Lastly, it's all about continuous improvement. Once we've launched our new smartphone, we'll continue to monitor performance and make tweaks as needed. It's this iterative process that truly brings DOE to life in real-world applications. So there you have it: how DOE can be applied to optimize a high-ticket item like a smartphone. Remember, the key is understanding which factors matter most and how they interact with each other. Thank you all for joining me on this journey through design of experiments DOE for process improvement. We've covered a lot together, from understanding the basics and importance of DOE to delving into advanced experimental designs like response surface methodology and Taguchi methods. We began with an overview of DOE and its crucial role in process improvement. Then, we explored basic statistical concepts that are fundamental to designing effective experiments. You learned about variability, measures of central tendency, and dispersion, which help us understand the impact of different factors on a process. Next, we discussed how to plan your experiment by defining objectives, identifying factors, and setting levels. We looked at various types of experimental designs, such as full factorial and fractional factorial designs, and understood their applications in real-world scenarios. The importance of randomization, replication, and blocking was highlighted, along with the basics of analysis of variance ANOVA to interpret results accurately. Graphical methods were introduced as powerful tools for DOE interpretation, including interaction plots and main effect plots. These visual aids help us understand factor effects clearly and make informed decisions about process improvements. Finally, we delved into advanced topics like response surface methodology and Taguchi methods for robust design, and discussed practical steps to conduct successful DOE experiments in industry settings through case studies. the most important takeaway is that DOE provides a structured approach to optimize processes by identifying key factors and reducing variability. It's about making data-driven decisions to improve efficiency and quality. Remember, the real power of DOE lies in its application, so I encourage you to apply what you've learned to your own projects or work environments. Wishing you all success as you embark on new endeavors with this knowledge. If you have any questions or need further clarification, feel free to connect with me through LinkedIn or leave a review for the course if you found it helpful.